AP Chemistry, we're going to continue with the answers to the day 24, or your sheet might say day 25. It's the second assignment from gas laws. And so we're going to go ahead and continue with that with problem number 6. And number 7 are really essentially the same. So we'll do number 6. So a mixture of air contains 0.78 moles of O2 and 0.22 moles of N2. That's actually backwards. It's really about 0.78 moles of N2 and 0.22 moles of O2, or 0.22 by percent. However, that doesn't matter. It's a problem. We're interested in the numbers, how the numbers work. Okay. So don't change that. That's okay for it to say it that way. Okay. The pressure of the air is 1.05 atmosphere. What is the partial pressure of O2 and partial pressure of N2? So I'll go ahead and write, I'm going to go ahead and work down here. You don't do this because you need this area, or unless you're doing it on a separate piece of paper. But let me just go ahead, because you're going to do this problem on your own. It's straight out of the video. So the partial pressure of O2, that's the way you would write it, equals, it's the mole fraction. So what is the mole fraction? It's the moles of O2. Okay, so it's simply the mole fraction of O2. That's moles of O2 over moles of everything else. In this case, there just happens to be 2 different compounds. So that's the mole fraction right there, times the total pressure. That will tell you how much of the pressure. It's just a proportion. Whatever the proportion of the moles of O2 to the moles of everything put together is, whatever that fraction is, and then you multiply it by the total pressure, that'll give you the pressure of O2. Gas pressures are a fairly simple concept. So what we're going to do is go ahead and write this. And again, we're doing this problem up here. Okay, these are all moles, but the moles are going to cancel out, and you're going to end up with atmospheres. So it's 0.78. 0.78 plus 0.22 is simply 1. So 0.78 divided by 1 is 0.78. So it's going to be 0.78 times 1.05. And that's going to give you 0.819 atmospheres. Okay, so of the 1.05 atmospheres of total pressure, about 4/5 of it, about 0.819, is going to be from the oxygen. Okay, for the nitrogen, all you do is replace that with the 0.22, and that gives us 0.231. Okay, atmospheres, and that's for nitrogen. And if you add those two together, it's going to give you the 1.05. Okay, so that's how you do this one. And again, as you saw, I needed more space. Maybe you want to do that on a separate piece of paper. This one's exactly the same, so I'm going to leave that for you to do. You got helium, you got hydrogen molecules. Now these two don't add up to 1, but you simply say, for you want to know it for helium, it's 0.62 over 0.62 plus 0.25. I'll set that one up for you and then leave it for you to do. Okay, and here it's measured in torr. That's fine. You don't have to convert that to atmospheres. Just give your answer in torr. That's a legitimate unit of pressure. You can't use it in the ideal gas law because the ideal gas law requires atmospheres. Okay, so do the math on that one. You'll get your answer. Same thing with H2. All right. Compute the molar mass of HECO2 and then use Graham's law. We did about 4 of those on the part 1 of this assignment, or in the first assignment of the gas laws. So I'm going to leave that for you to do. Go back and check the answers on those. Okay. All right. We're going to move on. Okay. So again, 10 is the same thing. It's Graham's law. Now, remember what Graham's law tells you. It tells you the relative speed of the lighter molecule compared to the heavier. How much faster is the lighter molecule going than the heavier? It doesn't give you an absolute speed. It doesn't give you something in meters per second or miles per hour. This formula does. It gives you an answer in meters per second. It's kind of an unusual unit variable for speed, but in this particular context, that's what it means. It's the speed of the particle in meters per second. So it's an absolute speed. It's not just compared to some other particle. Speed of the particle is u. Okay, so give the absolute speed of a particle in meters per second. What is the average speed of helium? So it's going to give you an average speed, because not all molecules, not all atoms, particles are going to move at the same speed. At a certain temperature, it's an average. Some move a little faster, some move a little slower. I mean, just think of obvious reason. The particles that are near the heat source, like the flame, they're going to move faster than the ones that are further away. But it's an average. All right, so there's the formula. Now, you have to use a different value of R. I believe this is the only instance in this particular unit where you have to use this unit of R. You will see that happen again in the future, and how do you know? It's just a matter of practice and experience to know which value to use. Okay, so that's why you have to practice your problems, not just do one or two, but really know them. Okay, so here we go. We're going to plug this in. So what are we given? Okay, so we're given a temperature. It has to be in Kelvin, and we know it's helium. So the molar mass of helium from your periodic table is 4.00. Okay, we just use the atomic mass or the molar mass from your periodic table. So we know that, we know the temperature, and we know the R. So we can go ahead and just plug in the numbers. Notice what replaces the mole Kelvin. It's a little hard to read. Mole Kelvin. There it is, mole Kelvin. On the bottom is the same as the other gas constant. But what's on top, the liter atmospheres becomes joules. That's the unit of measure. Okay, and the temperature here is going to be 300 K. It needs to be in Kelvin. And the molar mass is 4. We just keep it simple and put 4. Okay, so let's see how units cancel. Okay, anyway, I'm going to avoid the unit cancellation. I'm going to chicken out on that one. I'll tell you why. Because joules, I'm going to have to break that down into a bunch of constituent units, and I don't want to go there right now. It will give you, you have everything. If you chose everything with the proper units, it's going to work out. Okay, so trust me on that one. So do this however you feel comfortable. Calculate all of this. Write it down. Write down the number. I probably say to 3 or 4 places after the decimal. And then take the square root of that. If you feel comfortable doing it all on one big calculation, then that's fine. Okay, so we'll go ahead and do that. Okay, and what I get for that is 43.25 meters per second. So that's an absolute speed. It's not just compared to something else. It's how fast it's going in meters per second. Okay, number 12 is the same. All right. And 13 and 14 you can get from the video. But basically, diffusion is simply you have particles, and it's how fast they diffuse into an open room. That's diffusion. Just give you a quick shorthand. Effusion is a specific experiment. It's really meant to determine diffusion. And so you have a closed cylinder, and you have a plate in the middle, and there's a little hole there. And you got a bunch of particles on this side. The hole is a known size, and it's how fast are some of those particles going to wander over into the other side. And it's used to measure the diffusion of a gas, how quickly it will diffuse. Mean free path is the average distance between particles before they collide with each other. So it's a function of their pressure, among other things, and temperature and things like that. Okay. Purpose of van der Waals is on the sheet. It's basically, what if a gas is not ideal, and most gases we deal with in the real world are not. So it adds correction factors for PV equals nRT. So I'm going to ask you to write it. Go ahead and write the equation as well. Okay, that takes care of this video for lesson 2. For the second lesson, I should say, it's day 24. Your sheet says 25. Same thing. It's the second gas loss problem. And that takes care of that. See you on the next lesson.